Swayam Prabha. Digital India. Educated India.
Hello friends, I am Anjali Kulkarni, Principal Research Engineer at Center for Mechatronics, IIT Kanpur. Here we are starting with the experimental module on the course Robotics. So, till now you have listened to Professor Dutta through his numerous lectures on robotics, covering the theory and occasionally making use of a 2D manipulator to understand the basic concepts involved. There are many courses on robotics which are delivered. These are more of a rigorous mathematical excursion focusing the theoretical aspects. We see the laboratory training as an essential teaching and learning method for this interdisciplinary course. Hence, practical envision of the theoretical concepts are woven in the lectures. The course will have a practical orientation through laboratory experiments with the particular topics in hand. So, to begin with the experimental module, we thought that an introductory lecture on the basic electronics will help understand many concepts, and then later at the Center for Mechatronics we will continue with the lectures with the experiments on Puma robot and its architecture, its valve programming, stepper motor control, infrared digital and analog sensors, study of quadrature encoder and DC servo motor together with its control using Arduino interrupts, actuators and sensors interface with Arduino, and making of mobile and arm robots. Thank you. So, today we will start with the basic electronics module. So, introduction to basic electronics. With this lecture, we will now enter the experimental part of the course. This first lecture in this series will introduce you the basic electronics with its associated components and their working, which will be used during the experimentation. Nowadays, with advancing semiconductor technology, integrated circuits are available, tailor-made for many applications in robotics, but knowing the basic electronics concepts and components will help in analyzing and debugging a system under study. So, we will begin with the basic terminology and components. There are basically two types of circuits, mainly AC and DC. In robotics, we mainly deal with the DC circuits. Again, there are two quantities with that we like to keep track of in electronic circuits. These are voltage and current. These are normally changing with time, otherwise nothing interesting would happen. Voltage is denoted by V and measured in volts. It is the work done required to move a unit positive charge from the more negative point, that is lower potential, to a more positive point, that is higher potential. Equivalently, it is the energy released when a unit charge moves downhill from a higher potential to a lower potential. Current is denoted by I and measured in amperes. It is the rate of flow of electric charge past a point. We need sources to provide energy to circuits. Voltage source. It is a two-terminal black box that maintains a fixed voltage irrespective of the load connected to it. There is a limitation of maximum current that it provides. Batteries are the examples of voltage source. Current source. Similarly, current source is a two-terminal black box that maintains current across its terminals irrespective of the load connected to it. Normally, we use voltage sources in the form of batteries or regulated DC power supplies with no rated current and voltage. Kirchhoff's and Ohm's laws govern the functions of all the electronic circuits. Kirchhoff's voltage law, in short KVL, is the sum of the voltage drops around any closed circuit is 0, and Kirchhoff's current law, that is KCL, is the sum of the currents into a point in a circuit equals the sum of the currents out, and the power, that is work per unit time consumed by a circuit device, is power equals to product of voltage and current. Ohm's law states that the current through a metallic conductor or a resistor is proportional to the voltage across it. In equation it is V equals to IR. Resistor's symbol is R and its unit is ohms, is a passive device which obeys Ohm's law. Typical resistors are made of carbon films. Resistors have many applications. They are used in amplifiers as loads, in a bias networks, as a feedback element, voltage divider, etc. Capacitors and inductors are energy storage devices whose properties depend on the changing voltage and current. Resistors, capacitors and inductors, these passive devices connected in series or parallel form many circuits of applications, and these form nearly the basis of all electronic circuitry. Capacitors are used in waveform generation, filtering, blocking or bypass, used also in integrators and differentiators. Capacitors in combination with inductance makes sharp filters for separating desired frequency signals from background spectrum. A capacitor with C farad with V voltage across it has a charge of Q equals to CV. Capacitors and inductors have frequency dependent impedances or reactances. The rate of voltage change in a capacitor depends on the current through it, that is I equals to C dV by dt, and the rate of current change in an inductor depends on the voltage applied across it. In equation it is called as V equals to L into di by dt. You may wonder that how to see voltage and currents etc. in a circuit. So, for this we use measuring instruments. These are voltmeter, ammeter, these are old generator, old equipment of moving coil types, and nowadays we use multimeters and oscilloscopes. Multimeter is used to measure the static voltages, currents, resistances, capacitances, etc. Signals with respect to each other in circuits can be measured using oscilloscopes. Oscilloscope is used to measure the time varying voltage and currents. We will use these equipment while performing the experiments at the lab. Many a times you need to apply pulses or waveforms in the circuits. For this purpose, waveform generators or function generators are used. Normally, waveforms are the integral part of the circuits, but for testing purposes you need to have these waveforms generated or function generators which can supply variable frequency in sinusoidal, triangular, square waves or in pulses of different heights or time. There are electromagnetomechanical components which are used frequently. These are switches, relays and solenoids. The most basic electronic component is a switch. There are various types of switches. A switch is defined by two parameters, pole and throw. How? We will see in next slide. So, there are types of switches as called as SPST, that is single pole single pole double throw, DPST double pole single throw and DPDT, that is double pole double throw. So, in single pole single throw, a simple on off switch is there. The two terminals are either connected together or disconnected from each other, SPDT. So, this is called as single pole double throw, a simple changeover switch. There is a common terminal and it is connected either to L1 or to L2. In DPST, double pole single throw, so either they are open or they are close to both the contacts. Double pole double throw is equivalent to two SPDT switches controlled by a single mechanism. So, this single mechanism can connect to 2 poles at a time, and in the other mode this switches to other 2 points. Relays are extensively used. These are electrically controlled switches and they work on the based on the principles of Faraday's laws of induction. So, there are different types of relays: electromechanical armature relays, reed relays, solid state relays. A simple electromechanical armature relay is made up of coils and contacts. When the coil is energized by passing a current, the induced magnetic field moves the armature, which opens or closes the contacts. These are inexpensive, slow, bulky, noisy and have short life. These relays again have configurations like SPST, SPDT and DPDT. So, depending on the applications, we use a single relay or a combination of relays. Solid state relays. So, these are the switches based on the field effect transistor and bipolar junction transistor. FET switches are made up of several CMOS transistors. A voltage is applied to the gate, there is a control gate and which connects the source and the drain of a transistor network, that is load circuit. So, this drain and source, they are the part of the FET, which we will see in the next slide. So, these type of relays are fast, less noisy, low and high power applications are possible with these types of relays. Now, we will switch to analog electronics part. Semiconductor devices are the basis of the electronic circuits. There are passive and active devices. Diodes is the most useful passive device. Then there are transistors, field effect transistors and operational amplifiers. These devices have non-linear current voltage characteristics. Diode is shown as in the figure. It has 2 junctions, one is called P junction and N junction. P junction is called as anode and N junction is called as cathode. In the circuit it is shown like this symbol, a triangle and a vertical line, and sometimes it is also shown with this symbol. So, when this diode is given the forward bias, that is positive voltage is applied to positive terminal to anode and negative is applied to the cathode, then after a certain voltage drop, that is 0.3 volts in germanium and 0.7 volts in silicon, after that voltage the current, there is a drastic change in the current and this is called as the quadrant 1 or forward operating region of the diode, and this drop is called as a forward voltage drop. And in the reverse direction, when the negative is applied at the cathode, so there is no change in the current till a large value of voltage, but after some breakdown voltage which is of order of magnitude high than the forward voltage, one can see a negative current. So, these properties make diode very useful component and it can be used as a rectifier, Zener, power diode, there are Schottky diodes, then there are light emitting diodes which work on the photo conduction principles, which are used for indicators and display. Transistor is the most active component of the electronic circuits. This has 2 varieties, NPN and PNP. So, this is the symbol for a NPN transistor. There is a collector, there is a base and then there is an emitter. And this circuit here shows an amplifier configuration. There is a bias circuitry connected at the base and then a load is connected at the emitter and ground and a voltage source is given to collector with respect to ground. the family of curves can be seen in the red picture. For different bias current IB, increasing IB, we have while changing the IC is increasing and then it gets saturated. So, this is one operating mode, this is called as amplification mode, and then there are two other modes, that is cutoff mode. When IB is 0, VC is 0, and when with high feedback you have saturation mode. So, at that time IC is very high. So, these two modes, that is saturation mode and cutoff mode, are used as switches. BJT has the disadvantage of a low input impedance because the base of the transistor is the signal input and the base emitter diode is forward biased. Base emitter diode is forward biased. So, that possesses a low impedance input impedance. This feature is overcome in JFET. So, JFET is Junction Field Effect transistor. It is a unipolar transistor that uses an electric field to control the conductivity of a channel of one type of charge carrier. It is either N or P. With the reverse biased input junction, FET has a very high input impedance. For an N channel FET, the device is constructed from a bar of N type material with the shaded areas composed of a P type material as a gate. Between the source and the drain, the N type material acts as a resistance. The current flow consists of the majority carriers, that is electrons for N type material. JFET characteristics curves are shown in the figure. For a given value of gate voltage, the current is nearly constant over a wide range of source to drain voltage. The control element for the JFET comes from depletion of charge carriers from the N channel. When the gate is made more negative, it depletes the majority carriers from a larger depletion zone around the gate. This reduces the current flow for a given value of source to drain voltage. Modulating the gate voltage modulates the current flow through the device. So, this shows a transfer curve for a JFET. There are different varieties of FET. This is called as MOSFET, that is metal oxide semiconductor, that is provided between the gate, and this insulates the gate from the transistor. This situation further increases the input impedance, with the key advantage of that it requires almost no input current to control the load current as compared to BJTs, hence widely popular. Complementary MOS, that is NMOS and PMOS together make a complementary MOS, and these NMOS, PMOS and CMOS logic is built upon the MOSFETs, and especially CMOS are widely used in very large scale integration designs. Then there is another class of operational amplifiers. The concept of feedback gave birth to an ideal electronic device as OpAmp. It is a class of high gain DC coupled amplifier with two inputs and a single output. It has following properties. It has got high input impedance in the order of several mega ohms, low output impedance, the practical values vary between 20 to 100 ohm. It has high open loop gain, the practical values are between 20k to 200k ohms. This high open loop gain ensures virtual short between positive and negative inputs. Zero output offset, this is ideally 0, practical value is 1 millivolt, and then high gain bandwidth product. So, this high gain bandwidth product allows a large range of frequencies to be used without any attenuation. Many circuits are used in the systems. So, these are buffer unity gain amplifier, comparator, inverting amplifier, non-inverting amplifier and summing amplifier. and analysis of these circuits is performed based on two golden rules. The inputs draw no current and the output attempts to do whatever is necessary to make the voltage difference between the inputs 0. So, in the figure it is shown a buffer unity gain follower is shown. Inverting input is connected to the Vout, and based on these golden rules, whatever is Vn, the Vout is present at the inverting input. So, whatever is Vn, it is Vout. So, Vout is equals to Vin. So, this poses a high buffer, and there is a voltage comparator circuit wherein signal is given to positive input and non-inverting input, and inverting input is grounded. So, this is having a high gain. So, what the amplifier works in the saturation mode. Output is in either in positive saturation or negative saturation depending on the input. So, when input is positive, the output is positive in positive saturation, input is negative, output is in negative saturation. Inverting amplifier. Because of high gain and input impedance, inverting input is at virtual ground and output current is same as the input current. As inputs, they do not draw any current. So, I input is V in by VR, V in by R1, and V out is inverted with input current and R2 resistance into multiplied by R2. So, this gives V out as minus R2 by R1 into Vn. In non-inverting amplifier, because of virtual grounds, Va is equals to V in and Va is equals to V out and the voltage at the voltage divider circuit, that is V out into R1 upon R1 plus R2. So, V out comes out to be 1 plus R2 by R1 into Vn. Output is of same polarity of input. And then there is another very useful class of amplifiers, the configuration of amplifier, summing amplifier. Output current is the sum of the input currents. So, total I is the sum of I0 plus I1 plus I2 plus I3, and input currents, because of the virtual ground point, each input voltage appears across its resistors. Hence, input currents are I3 is V3 by R3, I2 is V2 by R2, I1 is V1 by R1 and I0 is V0 by R0. And the Kirchhoff's current law gives us total input current as I equals to I3 plus I2 plus I1 plus I0, and V out is inverted my current into R out. There are another useful configurations are differential amplifier. So, sometimes we need to cancel a common noise in two signals which we want to amplify. So, with this configuration a common mode noise is cancelled and we have V out, that is equals to R2 by R1 into V2 minus V1. Then there are integrating amplifiers. The output is the integration of the input with this formula, and in the differentiating amplifier the R and C, as you can see, they are inverted, and V out is the time constant into d voltage in by dt. That is the differentiation of the input. Then at points we need to convert current into voltage or voltage into current. So, with the OpAmps we can have these kinds of configuration. Here you can see the current can be converted into voltage as the voltage output as minus inverted input current into resistance, and in the voltage to current form we have this load current, that is the ratio of the input current voltage to resistance. So, this is a typical instrumentation amplifier. You can see that various amplifier op-amp configurations are used together to have further better qualities of the amplifiers. So, there are many signals which have signals in the microvolts range, and those need to be amplified. So, for those kinds of applications we need instrumentation class of amplifiers. These have robust differential gain. Input stage is having further high input impedance with 2 buffer grades. There is no common mode gain, and this can have differential gain. The gain stage is again having a differential gain which has low input impedance. And the overall amplifier amplifies only the differential component. It has high common mode rejection ratio, and high input impedance is suitable for biopotential electrodes with high output impedance. So, this is the application where these are mostly used. So, semiconductor devices are the basis of analog electronics. But until now we dealt with the analog circuit manipulations, dealing with the analog signals, those are from sensors, audio devices or measurements. But there are some signals having discrete values, example pulses from a particular detector or bits of data from keyboards or computers, etc. These are handled by digital electronics. So, digital electronics or digital circuits, they carry out combinational operations with basic gates and sequential operations with flip-flops. They invoke digital logic codified in the theorems of Boolean Algebra with hardware of different logic families like TTL families, CMOS families, and which may be implemented as integrated circuits. And these integrated circuits can be in the large scale, medium scale or very large scale. These digital circuits are used for data collection and control, which involves digital to analog and analog to digital conversions. And digital circuits are having characteristics, and these are the basic vocabulary which we will see now shortly, and use number systems and data protocols as alphanumeric coding for communication purposes. Digital circuits are inherently binary in nature, having 2 states, high or low, on or off, yes or no, etc. A binary number is a number expressed in the base 2 numeral system which uses only 2 symbols, typically 0 and 1. Each digit is referred to as a bit. So, how the integers are represented in digital systems? So, there are various methods. So, unsigned integers can be done in decimal like we do in the daily usage, then in the binary, octal or hexadecimal. So, these are easy, but how to tackle signed numbers? So, these present more problems and are addressed in various ways by using sign magnitude, offset binary, 2's complement, XS3, 4221 and gray codes. Number systems. So, as we have seen that there are 2 bits 0 and 1, 2 states. So, binary is the most suitable number system for the computers. So, number 1101, this is represented in binary 2 base, this is the least significant bit and this is the most significant bit. Like in decimal we use, for conversion we use 10's power, here we will use 2's power So, this 1 into 2 raised to 0 plus 0, sorry there is a problem here. So, this has to be 0, 0 into 2 raised to 1, 1 into 2 raised to 2, 1 into 2 raised to 3. So, this is 8 plus 4 plus 1, that is 13. There is another number system called as binary coded decimal. This each individual digit of the decimal number is represented by a 4-bit binary number, mainly for display purposes. So, 247 as a decimal number, this will be represented as follows in the binary coded decimal. So, 2 is 0010, 4 is 0100 and 7 is 0111. Then there is another hexadecimal system which is used to tackle longer or bigger numbers. Hexadecimal system is used. These are suitable for byte, that is 8-bit operations, and this is the organization of computers how they are made, and the numerals which are used for hex numbering system are 0 to 9, and instead of using 10, 11 etc., a single character is used through A to F. So, 0 to F. Example given, A9, this is represented in hex form, and in binary form it will be converted to, so A is 10, so 1010 in binary, and 9 in binary will be 1001. Then there is another useful class of the number system, this is called as gray code, and these are used for mechanical shaft angle encoders mainly. The principle here is that only one bit, that is LSB, changes from one state to the other. Suppose the previous number is 0010, then the next number will be 0011, and the next number, the number will be 0111. So, only one bit is changing. So, digital electronics is taken care by Boolean algebra. Boolean algebra is the branch of algebra in which the values of the variables are the truth values, true and false, usually denoted by 1 and 0 respectively. There are 16 possible functions. These functions involve only 3 operations which make up Boolean algebra: and, or and complement. We will see the circuits which arrive due to the combination of these functions. There are 2 types of digital circuit elements. These are called as combinational logic and sequential logic. So, logic gates, transmission gate and multiplexer, demultiplexers are the examples of combinational logic. Latch, flip-flop, counters and registers are sequential logic elements. As said earlier, there are 3 functions: invert, and, or, and or. So, these 3 functions together they form many gates. So, here we will see the truth table of these gates. So, invert, in invert logic gate, the whatever is input will be inverted. Suppose the input is 0, the output will be 1, and if the input is 1, output will be 0. So, in AND function, the output is 1 only when both the inputs are high. So, output is high when both the inputs are high or 1, and in the OR gate, so output is high even if one of the inputs is high or both the inputs are high. And NAND, which is denoted by the invert of AND, so it will be invert of AND. So, the outputs are high for whenever one of the inputs is 0, and output will be 0 when both the inputs are high. Similarly, for NOR, which is an invert of OR. You can see whenever both the inputs are 0, the output is high, and the output is 0 for all other combinations of the inputs. XOR is a very special class of gate, and it uses only 2 inputs, and the output is high when the inputs are dissimilar. So, for similar inputs the output is 0. So, these gates can be used to perform binary addition, subtraction, decision making, etc. MSI ICs are available with 2, 3, 4 or more input gate combinational function logic. K maps are used to solve the complicated logic functions using truth tables. And there is a useful circuit called as multiplexer, which is derived with the invert and OR gates. So, this particular gate selects between several analog or digital input signals and forwards it to a single output line. A binary address. So, these A and B 2 bits are used for addressing. So, 2 raised to 2. So, those will form 4 addresses used to select which of the input signals appears at the output. So, this is again called as many into 1. Example given for A and B equals to 0 0. So, this makes 1 and 1 here. C appears at the output. So, C appears at the output. Demultiplexer. This is again called as a data distributor. This takes a single input line and routes it to one of the several digital output lines. Other outputs are either held in an inactive state or open circuited. So, data will be available at one of these lines at a time depending on the address. A demultiplexer of 2 raised to n outputs has n select lines which are used to select which output line to send the input. So, latch, we are now entering the memory devices. Output depends on the previous state of inputs. As we have seen earlier, the combinational logic depends only on the current state of the input, but there are applications where we need to know the history of the inputs. Their solutions require some sort of memory. The typical tasks could be converting a string of bits in serial form into a parallel form or set of bits, keeping count of certain event, or giving one output pulse for each 4 input pulses as required in the sequencer of the stepper motor control, which we will see at the lab. So, there comes these memory devices into picture. As I said, output depends on the previous state of the inputs. So, the basic is a RS latch. This is a bistable multivibrator with 2 stable states, but for set and reset inputs equals to 0, there is a ambiguity in the output, because this 0 and this 0. So, that makes it 1 and this is not a stable state. So, this is eliminated by providing different solutions. So, one is clock D. So, there is one more AND state is AND gates are inserted, and data or the D input is given to a inverter. So, this avoids the eliminates the race condition. The truth table can be shown as like this: when set and reset are 0 and clock or control is high, then the outputs are the maintained as the previous outputs. There is no change in the output. When the reset bit is high and with the enable high, the output is 0 or the Q bar is 1. So, it is called as a reset state, and when the set is high, the Q is set to high, and when both the inputs are high, there is an ambiguity, as we say it is in RS latch. Then there are another inputs preset and clear. Those are inserted to have a particular kind of output when the circuit is switched on. So, flip flops, the basic block of counters. A J and K flip flop, which is the ideal memory element, has no invalid or forbidden input state of the SR latch, as we have seen earlier, when S and R are both at logic 1. There are two more inputs which can be possible, preset and clear, and here we will see JK flip flop, which has got J input and K input, and there is a clock input, and there are two outputs, Q and Q bar. So, when J and K both are 0, the output does not change, it retains the last output value. When J is 0 and K is 1, the output is set to 0, and when J is 1 and K is 0, output is set to 1, and when J and K both are set to 1, the output toggles, means if the last output was 1, with J and K 1, the output will go to 0, or if the last output was 0, then with J and K high, the output will go to high state. So, this can be understood with this timing diagram, and this is the internal block of the JK. So, here you see the clock pulses are coming at a particular interval. So, when there is a J high, J 1 and K 0, so this situation, the output is high, Q is high, and so with this rising, so with this clock pulse we have got output high. Now, with the second clock pulse, the J is 0 and K is 1, J is 0 and K is 1. So, the output is changing to 0 here. With the third clock pulse, J is 0 and K is 1, J is 0 and K is 1. So, the output continues to be 0. Now, with the before this high clock pulse is coming, J and K are changing their outputs, but change will occur only at the rising edge of the clock. So, this J and K is 1, and here the output is changing from 0 to 1, that is toggle condition. So, this is how the JK flip flop works. This JK flip flop has many applications. It can act as a shift register, it can be configured as a serial data transfer or parallel data transfer, it can be configured as binary counter or frequency divider and a sequence detector. Let us see a binary counter, how it works. This is built using JK flip flops. So, 4 flip flops are used. By taking the output of one cell to the clock input of the other cell. So, the J and K are held high. So, J and K are held high. So, with each rising pulse, the output will toggle. So, the clock is fed to the clock of the first, and the output Q is connected to the next clock. So, similarly, it is connected in the cascade. The J and K inputs of each flip flop are set to 1 to produce a toggle at each cycle of the clock input. For each 2 toggle of the first cell, a toggle is produced in the second cell and so on down to the 4th cell. This produces a binary number equal to the number of cycles of the input clock signal. So, same device is useful as a frequency divider. So, here you can see there is a divide by 2 in subsequent flip flops. And so, there is another class of register. Just a minute. Here. This uses D flip flops. So, it stores a binary word made with D latches, and there are some varieties are available with load and clear commands. So, there are 2 varieties of registers. One is serial in, serial out, and other is parallel in, parallel out. So, in, serial out, the same clock is fed to 3 D cells, and a serial input is connected to the MSB, and the consequent outputs are connected to the D inputs, and you have a serial output. And in parallel in, parallel out configuration, 4 FFs are used. Clock is same to all the flip flops, and parallel data, 4-bit data is applied to all 4 flip flops, and outputs are taken at the 4 outputs. So, that is in the parallel form. Analog meets digital. All these analog and digital components are the basic building blocks of the microprocessors, microcontrollers, computers, etc. Nowadays, digital hardware has become so powerful that tasks those seem well suited to analog techniques are often better solved with digital methods like digital thermometer, digital storage oscilloscope, etc. There is a classic 555 timer IC wherein you see the amalgamation of digital and analog technologies together. These are found in many electronic devices starting from toys and kitchen appliances to even a spacecraft. It is a highly stable integrated circuit that can produce accurate time delays and oscillators. So, there is a potential divider circuit, then 2 comparators are used, there is a flip flop, SR flip flop, and a discharge transistor output transistor, and there is a output stage. The voltage divider consists of 3 identical 5K resistors which create 2 reference voltages at 1/3 and 2/3 of the supplied voltage, which can range from 5 to 15 volts. Using the 3 pins, that is trigger, threshold and control, we can control the output of the 2 comparators, which are then fed to the R and S inputs of the flip flop. The flip flop will output 1 when R is 0 and S is 1, and vice versa. It will output 0 when R is 1 and S is 0. Additionally, the flip flop can be reset via the external pin called reset, which can override the 2 inputs, thus reset the entire timer at any time. With the external R and C components, we can achieve 3 modes of operations: monostable, bistable and astable. And we will be making use of this astable vibrator for generating clocks in many applications. One such application is a clock which is needed to move the stepper motor. Now, we will come to another section that is called as data acquisition. Why data acquisition? Because we are doing now computerized measurements and automation is needed. This is control of industrial processes and laboratory experiments. This calls for analog to digital conversion and digital to analog conversion. There are various types of signals and sources which we come across. There are digital signals and analog signals. Digital signals come from the switch closures, relay contacts, keyboards, computers, etc., and these can be TTL compatible interfaces and digital sensors. Analog signals come from the instruments, sensors, transducers, etc. So, before we start with the conversion, we need to first sample a signal. So, how it is done? Sampling means to convert a continuously varying physical value, pressure or strain, etc., into a continuously varying electrical signal. Amplitude range and frequency range are to be converted to digital values. Accuracy depends on the sampling rate, which is guided by Nyquist's criteria. The frequency of the signal should be twice of the sampling frequency, and another criteria is the number of bits used that will decide the accuracy of the sample. Here we can see there is a signal which is changing with time, making positive fluctuations and negative fluctuations, and we need to sample this signal. So, there are sampling pulses given to the signal, and at each sample level the signal is sampled. So, here there is no, so at this interval it is sampled, here it is sampled, here it is sampled. So, these are the instances when the sampling is done, but here you see here we have lost this information because there was no sampling interval, because the sampling was done slowly. So, this is how that sampling frequency needs to be decided based on the signal frequency. The sampling frequency was low here. So, how it is done? So, there is a class of circuits which is called as sample and hold, wherein amplifiers, OpAmps are used and MOSFET switch is used. Basically, it is represented by a simple connection like this, open switch, a switch connected to a capacitor. So, switch in series with a capacitor, digital MOSFET switch is used, which has got low output impedance resistance. That is why the capacitor gets fully quickly and fully charged. That depends on the resistance RO and RDS on of this MOSFET and the C value. High input resistance of A2 maintains the charge on C when the switch is open. So, there is no leakage, as these inputs they do not draw any current. So, the charge is maintained, and the capacitors need to be made with mylar, Teflon, dielectrics to hold the charge properly. There are various types of DACs and ADCs. The data acquisition uses binary weighted R2R ladder techniques, and analog to digital conversion uses counting or digital ramp, tracking, successive approximation and flash ADCs. These DACs and ADCs use analog and digital electronics together to arrive at a technique. Many off the shelf data acquisition cards are available in the market. One need to choose them wisely. Following are the few criteria of the selection for ADCs. You need to see the precision, speed, accuracy, required supply voltage, analog voltage range, cost, computer compatibility, ease of programming, and you have to see the trade-offs between these one or two together. There are some special purpose ICs which we very commonly use in robotics. These are H-bridge driver IC and a servo controller IC. So, here you see a H-bridge IC which is built in, and this is widely used for DC motors and here is a servo controller which takes care of the feedback and motion control. So, now coming to the end of this lecture, this presentation covers the important basic electronics theory and its related components widely used in robotics. We will be using many of these devices during our experimentation at the Center for Mechatronics. Nowadays, special purpose ICs are available off the shelf, but knowing the basics of electronic devices help in analyzing and debugging electronic systems in hand. So, the literature which have been used in preparing this presentation is the book on microelectronics by Millman and Grabel, Digital Computer Electronics by Malvino and Brown, and the Art of Electronics book by Horowitz and Hill, and many of the concepts are taken from Hyperphysics website. Thank you.